Hi everyone, welcome to our event tonight. I'm Jess Hargreaves. I'm a PhD student up at RSES, and we just really want to welcome everyone first off in person and online as well. A quick housekeeping thing: if you could chuck your masks on just while we're inside here. The campus is a mask zone, and the bathrooms are just behind, and the fire exits just off the stairs. Before I officially get started, I just want to acknowledge the traditional custodians of the land that we're meeting on today, and that's the Ngunnawal people. I wish to acknowledge their hand respect, their continuing culture, and the contributions that they make to the life of this city and this region. We'd also like to acknowledge and welcome other Aboriginal and Torres Strait Islander people who are attending today's event. And to get started, we invite the VC, Brian Schmidt, up to welcome us all. Yeah, thank you.
All right, well, it's great to see lots of our scientists back all together again, and thank you, Jess, for your acknowledgement to country. I would like to welcome everyone, including our guests from up north. It's great to have you here, and it is wonderful to see everyone trying to get back into the swing of things in the, what I won't quite call post, but the near post-pandemic world. I really appreciate being able to have people come down and be part of what is ultimately meant to be a celebration, I think, of our sciences. And it is absolutely worth celebrating. It's something that Australia has done so well for so long. I'd like to welcome our guests joining us online. And I think back to my earliest childhood fascinations, and I was always going to be what I thought was going to be a meteorologist. I decided that at about the age of 3. And what I was really interested in is what we would call climatology now, but it was not described as a subject back in 1970 or whenever I started thinking about this. But the other thing, I really enjoyed trying to go out and understand the geology and looking at the rocks and the formations and things. So this is a huge part of my early scientific interest, probably more so than astronomy was, actually. So it is a subject that is of immense human interest, and I think we sometimes forget that science started not because it was useful, but because it was interesting, and then it often turned out being useful, and that's still that way today. And so the subjects that you're working on are of intense interest to people around the world. It is, of course, the world we live in. It's a beautiful subject. It's hard, it's complex, but of course it is also useful. We are looking at a continent that we live in, which our distinguishing feature is mineral exploitation. We're going to be looking at carbon sequestration. We're going to be looking at hydrology, all these things that make up earth sciences. And then there's the whole issue of understanding climate. And again, that brings the ocean and the atmosphere together. And it even, of course, intersects with my own field of astronomy. When we start trying to understand planets and the outer solar system, it is quite a remarkable intersection. Of course, here at ANU, being able to detect tiny parts per bazillion of rare isotopes that happen to occur because of things like supernovae going off in the distant past, and being able to make measurements like that, it's astounding how it interacts. So Australia, as I said, has been home of many of the leading earth scientists and departments in the world. I believe there are at least 5 universities that are seen to be in that discussion of what we call the top 50. Now, I have a little bit of cynicism about trying to rank and everything, but any way you look at it, we are an incredibly important part of the world subject of earth sciences, and it's not surprising that we have, one of the most efficient mineral extraction industries in the world. And that's not a bad thing. That is so efficient. Earth sciences will continue to play an absolutely critical role in the future. And so it's really important that we look after it for a whole range of reasons. And so I will be advocating on your behalf. And I've sat down and talked to both sides of Parliament and saying the research system in this country is broken. And you do not realize that we cannot properly fund things like earth sciences, like physics, like chemistry right now. And so we are losing this amazing capacity that we are going to absolutely need more than any other time in our history. So I will be out and continue to advocate on your behalf because the work that you do is absolutely essential. It's, I think, probably poorly understood. And I don't know, I guess that people just assume that we make progress without actually putting work in beforehand, and I find it quite astonishing. And as I said, I think we do intersect a lot within the climate change space, and we've seen, and we're, unfortunately, we're all living the experiments these days, especially our friends from Brisbane. If you happen to have your house in the wrong spot, I hope it's on stilts. And I'm afraid you're going to keep on doing that experiment. And I don't know how big we can make levees, but we're going to have to make them a lot bigger than they are today. But as I said, we go in all sorts of areas with respect to the earth and the oceans. Developing the new techniques that will reduce the impact, for example, of mineral extraction is something we're trying to help doing here. And we're also trying to look at, how are we going to create the critical minerals that we need to create the wind generators, the solar voltaics, the batteries of the future so that we can be sustainable. And it's a cycle. And I think that the fact that Australia has been so amazingly good at extracting minerals in what's probably the least invasive way of anywhere in the world, relative to the impact in society, it's something we should be proud of. While we're focusing on addressing the challenges of the 21st century, I think it's worthwhile thinking about what we've done in the past. And one of the things I'd like to highlight is that earth sciences is a place where we bring the world together, and we're always trying to invest in the future. It's just great to be able to see people creatively go through and do something that is fun, but at the same time is all about being able to take very complex things and explain them. And as I was trying to explain to the APC, that's important because when you can explain really complicated things very simply, it means you really understand them. And that often gives you insights into how to solve the next problem because you have such a deep understanding. Earth sciences has maybe not one of the foundation subjects at ANU, but it has a history right back to the very early times here. It is our 75th anniversary, which means we are a very young university. But we have decided to do a whole year of celebrations, especially since we lost the first half of our 75th year. And we've been wanting to kind of share some of the stories. And stories, I want us to think about the stories maybe you haven't heard. So let's talk about Jermaine Joplin. If you've seen Joplin Way down in Cambridge, this is named after her. She had an international reputation for her research in petrology in New South Wales. And her pioneering work, unfortunately, didn't translate. And this is the same old story these days, but slightly even more challenging in the past. She couldn't turn it into a long-term professional job. So to get by, she did social work while teaching in geology. So, things are tough when your side job is working in social work, because we know what a high-paying job that is. But in 1952, she secured a permanent research position at ANU in the newly formed geophysics department. now known as RSES, and she worked with none other than John Yeager and Professor John Richards. Over the next 16 years, she supervised PhD students, compiled chemical data on Australian rocks, and wrote highly acclaimed textbooks on Australian igneous and metamorphic petrology. The rock physics research she did with ANU Professor Mervyn Patterson underpins our contemporary understanding of the movement of the continents. And this field of research continues to be relevant today, well into the 21st century. So it is great that we have stories like that, and you will find these hidden stories of women that we're trying to elevate because they haven't been listened to and thought about as much as they should have. And of course, that was under a situation where you typically had to give up your job if you got married and or God forbid became pregnant, as people found. But the work that we do continues to be in this country absolutely leading edge, and that's why it's so great to be able to have people come together, celebrate it today. And I will now hand back without much ado to Jess and Mark, where hopefully we'll get on with this amazing panel. But I'm going to leave you as we finish with one quote from Jermaine, which she made in 1968. When I started in the 1920s, early 20s, girls were not supposed to go wandering about with maps and sacks of rocks. But if you were really interested in your work, you had to. And that is exactly what she did, and what all of you do to this day. Thank you very much.
Thank you very much, Brian, for that. Welcome, everybody. My name is Mark Hoggard, and I'm a research fellow at the Department of Earth Sciences here. I'd also just like to say hello to everyone online. You are also a big part of this meeting. Thanks for joining us. If you have any questions, we have a Q&A function on the Zoom chat, so please type them in there. You can upvote them and so on, and later on there'll be an opportunity to ask them to our panelists. Okay, so everybody who's already spoken has already done a very nice job of kind of motivating why we're here tonight, so I can probably flip through these quite quickly. But I thought I'd just start by saying what the breakdown of our attendees are tonight. So we had about 270 people registered for the event, dominated obviously by academic backgrounds, but we also have people here from government departments and people working in industry and education as well. So welcome all of you. A little bit about what we'll be hearing about. So I think we'll be hearing about probably something about seismic hazards that go hand in hand with things like tsunamis and also volcanic hazards. We're probably going to hear something about climate change. As everyone knows, global temperatures are steadily rising.
Can you share screen?
Oh, sorry.
Oh my gosh. Sorry, everybody. As everyone listening.
Is that good? Okay, sorry about that. Yes, we're going to hear about climate change. The steady rising global temperatures is leading to observed melting of major ice caps, such as those over Antarctica, and observed rises in sea level. We've probably experienced quite a lot in our lives in Australia, extreme climate events. So going hand in hand with climate change are a more chaotic climate. It includes things like large-scale flooding, bushfires, and drought. Another area of earth science research that kind of is relevant to drought is to do with groundwater. So Australia pulls about 20% of its water out of aquifers, and these systems are formed in sedimentary basins, and they are something that we generally try and understand, at least in part, from a geological perspective. And the final thing, which we've already heard a little bit about, and I'm sure we're going to hear more about tonight, is critical minerals. As time has gone by and technologies have developed and humans have tried to diversify things like, for example, how we generate power, we are using increasing amounts of all the kind of nice, exciting, rare things that lie down the periodic table and supplying those in a kind of stable way is a big part of where we're going in kind of modern geoscience. And so understanding how we find these minerals, how we get them out of the ground, is a big part of the work we do. So I thought I'd just put this up because I always put this up in talks. I like to bang on about a lot, but I kind of use these a lot for kind of reference and writing proposals. So in 2015, the United Nations released these 17 Sustainable Development Goals. These were goals that were kind of, the idea is we as human beings across all societies should be striving towards achieving. And I think a lot of the work you're going to hear tonight fits into various of these different goals. I had to put one slide up like this. Earth science in general, at least in terms of undergraduate numbers, has been in decline for a few years. So the graph is showing you the number of undergraduates enrolling in Australia in blue, UK in red, and in green the United States. And you can see that there has been a kind of drop off, generally speaking, in numbers over the last kind of decade or so. Going hand in hand with that, here in Australia, we've had reductions in federal funding that's used to support earth science research in academia and so on. And we've also seen the closure of several prominent earth science institutions. So this is kind of, against this backdrop of earth science is clearly very important for a lot of things we're facing in society, there is this kind of problem of reducing numbers and funding. So tonight, what we'd like to try and do is answer the question, what is the role of earth science research in 21st century Australia? And then the kind of sub-question for that, which I'd also like to ask is, what do we need to ensure we do moving into the future to ensure we maintain a healthy, vibrant and sustainable geoscience community? I'd like to welcome our 4 expert panelists who've come from far and wide to join us. Thank you very much. We have Helen Degeling from the Geological Survey of Queensland. We have Melanie Finch from James Cook University, Matt England from the University of New South Wales, and Will Howard, who's joining us. He's actually based in Canberra. So thank you very much for joining us. First up to talk tonight, we have Matt, if you'd like to come up and take it over.
Thank you so much, Mark. Thanks, Mark. Thanks, Jess, for organising this. And thank you, everybody, for turning up tonight here in the theatre and also online. Great to see you all. Great to talk about this topic. Go to my first slide. So, as Mark said, I'm from University of New South Wales. This is nice photos, one from my workplace and one from the beach I like to swim at down at Coogee. It's fun to be at the university as a researcher there. My interests I'll talk about in a minute. It's great to visit you here in Canberra. I love the cooler climate. So just to give you an understanding of where I'm coming from, I am an earth scientist, but I'm also really foremost a physical oceanographer. And then in time, I've sort of, a bit like Brian's description was nice, the physics of the oceans are not too different to the physics of the atmosphere. So I'm going to call myself an atmospheric dynamicist these days because I work on that topic as well. It's just naturally you're drawn across to it once you start working on ocean dynamics. And before you know it, you're a climate scientist because ocean warming is dominating the climate response to greenhouse gas increases. 93% or so of global warming is found in the oceans. So these days you can't really be an oceanographer without being a climate scientist. And so this is my academic journey is kind of along the lines of this sequence of topics here, from the physics of the oceans into climate science. Just a bit about the field. It's in earth sciences, but it's also kind of in physics and it's kind of in maths. If you go around the world looking for where oceanographers sit in universities, they're not always in an earth science department. They're sometimes in the physics department, they're sometimes in mathematics, sometimes in earth and environment. It varies. It's a highly theoretical, very numerical topic. We do basically solve equations for a fluid on a rotating sphere of a stratified bit of ocean or atmosphere. So that's why people at RSES, for example, who I work with, all of them are solving equations, and they do that because they want to understand the system really at a deep level. And these basic equations that we know govern the system, we've got laws of physics basically that define the movement of the oceans and the atmosphere. That's a big advantage in the field of science we're in, to have equations that perfectly describe the system. The challenging thing is that they can't be solved analytically, so we've got to go to either big computers combined with observations. And so there's a lot of work to be done in this area. We don't just look at equations, we go and make measurements. So a lot of our students go into the field, go onto research vessels, trek across the global oceans. This is the biggest experiment ever undertaken by humanity, apparently. This is the World Ocean Circulation Experiment. It lasted a decade, cost more than any other previous experiment. And the goal was to traverse the ocean in this sort of enough resolution to get a really good estimate of the base state of the oceans in the 1990s. Today we have remote sensing satellites, drifters, moorings. This bit of ocean sciences is a lot of fun. And whilst I'm mainly a theoretician and a numerical modeler, I love this stuff. And I couldn't wait to go to sea as a PhD student, as a postdoc, because this is the real stuff, right? This is when you're actually measuring seawater, measuring properties, understanding the system that you're working with, that guides our theoretical understanding. And so back to the topic of tonight, we're talking about the future of our sciences. And if you imagine sort of turning to Earth as an alien to look at this planet you've discovered, you kind of wonder why they call it Earth, right? Why didn't they call this ocean? It's just dominated by ocean. And so to study our Earth, we can't avoid studying the ocean. It's a profound part of our system, not just 75% of the surface area, but like I said before, as we warm the system with greenhouse gases, the oceans are sucking up heat and carbon at a profound level. It's kind of seems free of charge that it's absorbing heat and carbon. Of course, it's not, because down the track we have payback with sea level rise and oceans acidifying and intensification of tropical cyclones and so on. So yeah, as an ocean scientist, in a way, our field got hijacked by the fact that we're burning fossil fuels at an absolutely crazy rate. When I say hijacked, I got into the field not to be a climate scientist. I really wanted to understand ocean dynamics, but before I knew it, I had to go and write IPCC reports with lots of other people and understand this big perturbation. We're powering the planet with greenhouse gas emissions going through the roof. We had warnings of what was going on a long time ago, and you can see the trajectory almost would look like no warnings ever happened. If you look at the trajectory of carbon emissions globally. And so we have an enhanced greenhouse effect, and that's warming the oceans, it's intensifying cyclones, it's intensifying the hydrological cycle. Bushfires are not so much part of the oceans, although the oceans do rearrange weather systems, and that heat extreme you get is really just from trapping greenhouse gas heat in the atmosphere. But it's a burgeoning field. And so within our sciences, the slide that Mark showed, that's very confronting about decline in enrollments, that's concerning if the climate trajectory is that way as well, because we've got a big problem on our hands. Lots of things are changing, and we need very skilled and capable, numerically talented people who've got physics intuition, earth science graduates coming through to study this problem, to help us adapt to it, to help us reduce emissions through new technologies, capturing carbon and storing it, or which I'm still terribly skeptical about, but maybe somebody can convince me today it's possible. But there's a lot of work that needs to be done. Because we've created this problem of emissions, this is a huge growth industry to address the problem and to adapt to it. And so I just want to quickly show a couple of slides. I'd love to get a 5-minute warning, Mark, because I don't want to go for too long. But one of my colleagues at UNSW, Danielle Courbaste, approached me about a month ago and said, hey, I'm looking at 150,000 papers across climate research over the last 30 years. I want to understand trends. And he started showing me diagrams like this, which is hard to see at that scale. So I'm going to zoom in a bit. And he's looking at the trends over just the last 30 years in this topic area, based on keywords and based on statistical analyses that I'm still just getting to grips with in collaborating with him on this topic. And one of the strong things is just the growth of the field. I'll replace it with this slide here. In 1990, I was a second-year PhD student. And back then, about 2,000 papers published in the topic of climate change. And in just that 30 years, it's a tenfold increase out to 25,000 or so. Don't worry too much about the details here. So it's an exploding field in terms of research output, but it's also evolving. It's not just a matter of this field increasing in its presence in science and the need for us to do it. There's also some very important changes. Things like mitigation was, this was a chart here from the most common keywords to it goes down to 1,000 different terms. I'm just showing you the top 15 or so here. And things like mitigation have just shot up to here. And I mean, and things like agriculture are turning out never up in the top 15 before. There's big changes. Things like precip and temperature are maybe on the decline. And there's a lot of a storyline here. The more you stare at this, the more narratives there are in this diagram. I would say what it's telling me is that we've made big advances in the science. And so the percentage of work being done on the science of the problem is probably declining in relation to solving it. That's not a bad thing, because we do know enough about the basic problem we have that we need to get onto the science around adapting and mitigating. They're the big things we need to resolve. And I can say that without any conflict of interest, because my field is the one that's there, just creeping down a little bit. Of course, we do need the science still, because we can't adapt blind. New South Wales put in a desal plant, and they probably never needed one. It cost $2 billion. They didn't do any climate research to see if that was worth building. The West Australian government, I don't even know which government, Liberal or Labor back then, did it. They had a desal plant on the radar. They did some science behind it. That $2 billion investment was absolutely essential for West Australian drinking water. Good investment, good science behind it. So I'm not saying science is going to decline, without end. It really is needed to adapt properly to the problem we have. My good friend Naomi Reskis made the point that maybe the IPCC has done its job, and I think she has a point here that the science is established enough that we can move on to the adaptation and mitigation side of the problem. I see Mark's got up from the chair, so I want to finish up on a different narrative, and it's coming back to the solid earth sciences just for a little bit. And that is to say, even though if I had my way, we wouldn't teach another student on this planet where coal and fossil fuels are located in the Earth system, because we don't need any more of them in the atmosphere. But that's not to say mining is going to be gone. This lovely analysis by Martin Green from UNSW, he sent me his slides. We're going to see a big change in the energy composition that we power our planet with. But this energy transition to solar won't mean this idea that the Australian mining sector will be killed off by this transition is completely unrealistic and untrue, because I think, as Mark showed a slide before, there's going to be a whole bunch of other mining sectors that grow up. The coal mining should be closed down, but we need a whole bunch of things to create the solar cells that will power us at low carbon cost. And so here's the decline in cost in coal and oil and so on, and there's a big increase in the need to understand the mining of those precious minerals. And so mining will live on. Okay, thank you.
Next up we have Melanie Finch from James Cook University.
Okay, thank you so much. It's really wonderful to be here with you. So as well as being from James Cook University, I'm also the president of an organisation called WMESA, Women in Earth and Environmental Sciences Australasia. So tonight I'm going to be talking about the earth science of the future, but I'm also going to talk about the future of earth science, and I'll explain a bit what I mean by that as we go through. So first of all, what do I work on? So my research is about ductile shear zones. So you're probably all familiar with major fault zones, so the San Andreas fault or the Alpine fault in New Zealand. So those are what happens when tectonic plates, you have a tectonic plate boundary, and that's at the surface where rocks fracture and break. But when you're deep inside Earth, rocks behave a little differently. So instead of breaking and fracturing, then the crystals can actually change shape, and they can actually deform in this sort of this way that rocks actually flow. So that's what you can see here. So we've got this white layer, and it's offset to the left up the top there by this ductile shear zone. So that's what I love to study. Ductile shear zones are really important for us on Earth because they're at every tectonic plate boundary, and they have a lot to do with what we see at those plate boundaries. So at tectonic plate boundaries, we see a lot of natural disasters. So one that we sort of see a lot is earthquakes. So where one plate is subducting under another one, there's a shear zone between those two plates accommodating that movement. And every so often that a sudden movement on that shear zone will create an earthquake. So we see lots of earthquakes in subduction zones like that. We also see lots of volcanoes. And we know that understanding volcanic hazards is really important in our local area. Maybe not so much in Australia right now, but in our, a little further afield. So New Zealand, we'll remember White Island, Tonga more recently. And with that also, with earthquakes and these volcanic hazards, comes the risk of tsunami as well. So there's lots of people in Australia working on things to do with these natural hazards. And that's going to be really important for earth science going into the future, to keep working on these questions and understanding our local area a lot more. So that's a big area for growth for Australia. So shear zones, my favourite topic, are also really important in this context. So this might look quite ugly to the untrained eye, but to a geologist it's very exciting because it's a lot of outcrop, which is awesome. So this is a mine, a rare earth element mine in Mount Isa, so in the Mount Isa region. And I was there on Sunday. This photo is just from Sunday. And what we see there is we have this rare earth element deposit, and right next to it is this shear zone. So I love studying shear zones because I think they're super cool and really interesting, and it's amazing how rocks flow. But they also do things like this, create ore deposits. And we really care about rare earth elements because they're the things that go into our wind turbines and our solar panels, electric car batteries, and that's something that Helen's going to talk about a bit more later on. So yes, I was there in the field with my student, Alanis. She's doing her PhD on this area. She's doing an awesome job. And we had a really wonderful time. And when I think about the future of earth science, Alanis and people, the students coming through now, they are the future of earth science, which is kind of weird to me then that when we're heading into the field, we had a lot of weird comments from people. So things that I've never heard before, like, what, 2 women in the field? How are you going to do that? How are you going to sample rocks? It's like, well, I just like begging disbelief, right? What year are we in? It's just crazy. But this is more than one person who said this sort of stuff to us. And it's awful that that's still where we are. That's the first time it's ever happened to me. But I have my undergraduate students telling me that sort of everyday sexism happens to them as well. And it's not just in geology, it's in fisheries, it's in lots of different disciplines. In gender equity in earth and environmental science. So in 2020, we wrote an article about the state of gender equity in geoscience in Australasia. And in that article, we explored the nature of the problem, so what it actually looks like, and what some of the causes are and the solutions as well. So it's good to be constructive. So, and the nature of the problem kind of looks like this. So here we've got the proportion of male and female students in university. So we've got the bachelor degree and postgraduate degrees, so PhD students up there. You see it's about 40% women. And that 40% women is retained into like the earliest levels of academia. So here's academics level A, and there's about 40% women there. So that's the postdoc level straight out of PhD. You can also see that in the mining industry, we have a similar sort of proportion there as well. So this is all from census data, and there's no easy way to break this down, which is why this is based on age. You kind of use that as a proxy, I guess, for career progression. So what we see from those early stages is that the proportion of women drops right off until at the highest levels, at professor level, level E, and at the highest levels, like presumably within mining companies, we're seeing less than 10% women. Women are leaving our industry. And this is not a sustainable thing for our industry, like if we're going to have, earth science of the future and we want a viable future of earth science, we need to stop this. So there's reasons to believe that it's not stopping, it's not slowing down. People tell me that it's getting better. It feels like it's getting better some days. But then I was looking at this census data, and it's over time, this is as far back as I can get, and it sort of shows the proportion of women, which is these numbers here, is kind of staying around the same, like 35, 38, I don't know, is it going down? I'm not sure. So we'll see when we get the next set of data, hopefully in a couple of months. So I think we need to be doing more. What are the problems? What are the causes? So what's happening here? Well, basically, men are hired, promoted, and retained more than women are. So, it sounds quite obvious, right? So why is that happening? Well, part of the reason is that there's bias against women in hiring and promotions. So these unconscious biases that feed into our decisions. So we can make those processes more objective, and then hopefully that will translate to keeping more women. Women also report a chilly climate, and this comes out in the research on this topic. Women have more negative experiences than men, so the everyday sexism like me and my student experience, and just that erodes your sense of belonging, your self-efficacy. And these sorts of psychological factors are really important for keeping people in these jobs. Feeling like you belong is really important. We also see that women tend to shoulder the burden for caring roles, and that's exacerbated by this unequal division of parental leave. So not at ANU. ANU's doing an awesome job. They've got 26 weeks parental leave for either parent, but that's not the case in a lot of other places. So in a lot of other places, the birth mother will have really generous parental leave, and the other parent will only have a couple of days, even if they're the primary carer. And so that just sets up households for being really unequal, and that translates into the workforce as well. So that's another area where we need to improve. And of course, we have to mention that in industry, we're seeing, the data come out now, and like a quarter of women are experiencing sexual assaults in those jobs, sexual assaults, and 60% are experiencing harassment. That has to change before we can hope to retain any women in that field. Absolutely, you can't go to work and be hurt. That's crazy. So for the future of earth science, I think we really need to be looking at some of these things and fixing those so that we can retain and hire and promote the best people going into the future. Thanks.
Thank you, Melanie, for your considered words. Next up, we have Helen.
Well, hi everyone. It's great to see some familiar faces here this evening and also some new ones. I will admit that I, like the others, have tailored my talk more to a non-geological community audience. So for all the geologists and geoscientists in the room, close your eyes and a 5-minute nap. I won't be offended, I promise. So I'm Helen Degeling. I'm the Director of Minerals Geoscience at the Geological Survey of Queensland. And while I currently work in government, let me just move a little screen here for a second. While I currently work in government, I did spend about 12 years out in the mining industry and doing exploration. I was looking for things like copper and gold. I got pretty sweaty, I got pretty dirty, I swallowed an awful lot of flies. It was great. I learnt about how do you figure out what it is that lies beneath our feet, and then how do you get it out of the rocks that it's sitting in. So it's a really, really good learning curve coming from a more academic background. Oh, I switched to the next slide, sorry. Apologies, I've lost my place. Before being in the mining industry though, quite a few decades ago now, as it turns out, I actually did my PhD right here at ANU. So it does feel a little bit like coming home tonight, although the number of faces that I know are getting smaller and smaller. So there's only a couple in the room here that I do know well. In my role at Queensland Government though, I head up a team of very nerdy geoscientists, and we work to understand the mineral endowment and the mineral potential of our state. But more importantly, it's actually my role to understand what government can do to facilitate the change for the mining industry towards a low emissions and a decarbonised future. So to achieve that, we have to know what it is that we actually need as a society. If we could go out and we could build all of the green energy technology that we need in order to completely turn off all those coal and gas-fired power stations that Matt was talking about a moment ago, we need money, okay, put that aside. We need lots of cleared land for all the solar farms, all right, we've got that. We need infrastructure, we need resources to do that, but we also need some pretty specific raw materials to build that technology. You've probably guessed, and Matt alluded to it before, that the picture I'm showing you here, which is from the International Institute for Sustainable Development, I'm going to talk to you about the metals that we need to actually make this technology and to achieve that transition. 3 examples that I have here are solar energy, wind energy, and electric cars. All right. Could you hear me before or not? Yeah. Yeah, good. Okay. Online. We love the online. All right, linking all of these 3 systems, they are all made up of the elements plus many more that you can see on this graph. But then linking all of that, there's going to be a lot of copper wiring to get the energy that we're generating at those solar farms or wind farms to the places where we need to use it, like our cities, our homes, our industries. And then once we've got it there, we actually need a way to store it so that we can use it. So that means large grid scale batteries, which then have a whole other suite of chemistries as well. We have a lot of these materials in Australia. I won't go through all of that. Iron, aluminium, we have in abundance, a few other things. There are some that people may have heard of in the media, cobalt, lithium, nickel. Those are the things that we commonly need in lithium-ion batteries for electric cars. But what about things like tellurium or indium or gallium or germanium? The things on the periodic table that, the average Joe's never heard of. They may be less common, or they're less commonly produced, at least, but we do know where to find them. However, knowing where these metals occur and then getting hold of them is not always quite so straightforward. To reinforce the point of the metals that we need, here's another snapshot of everything that goes into different types of energy systems. I'm going to highlight here the energy storage row, which is basically batteries. And you can see that there's quite a variety of different metals that go into the different types of batteries. There's about 11 of them. I won't read them all out. You can also see some of the things by comparison. Copper, which is the vertical one that I've highlighted, is essential across the entire spectrum of energy solutions. Nickel is another one that is almost as broadly used. So this leads to huge forecast increases in the demand for particular metals as the energy transition gains momentum across the world. So as I said, we do know what we need and we're pretty good at finding it. But where it comes from and how we get it is just as important as what it actually is. So here's an example of cobalt, which is again used in lithium-ion batteries for electric cars. The world's largest resources of cobalt sit in the Democratic Republic of Congo. In that jurisdiction, mining is quite poorly regulated and child slavery is quite a real issue. So there may be a dark side to your shiny new Tesla. What about rare earths? We hear about those in the media as well. There are about 17 of them. They make very powerful permanent magnets. They're very important components in wind turbines. in electric cars, in defence. I think a jet fighter has about 400 kilograms of rare earths in it, so that becomes a political issue. But traditional methods of extracting rare earths from rocks and then extracting them from each other, because they kind of like to stick together, requires a lot of energy. That energy may not always be sustainably produced. And it also requires a lot of things like acid, which is, not necessarily a good thing. China, you can see on this graph, has dominated the global supply of rare earths for quite some time. That is now, in more recent years, starting to even out because of that political security related to defence that I mentioned. But historically in China, the industry has been poorly regulated, and in the rush to dominate the rare earth market, some Chinese companies have caused massive environmental damage in some areas. So the reality is that these issues are well known. They're well documented. Governments around the world are taking action. So are investors, investment houses, communities. It's the sort of thing that there is a lot of action on. There's a lot of work underway to ensure the ethical sourcing of materials for green technology for European car makers, for example, with the introduction of the European battery passport, which will be legislated in 2026. But that speaks more to the policy end, and it's my job this evening to emphasise for you the ongoing role of the resources sector in the energy transition. So here is a graph. Some of you may have seen it before. I borrowed it from Richard Shoddy at Minix Consulting. It does date back to 2017, so it's a bit out of date now, but I wanted to include it because it tells such a profound story. And I really don't think that the broader trends have changed much in the last few years. So if I can make the pointer work, is that the top button there? Yep. What we've got is up until this dark blue line here and back this way, we're showing the historical demand for copper throughout, recorded human history. And then up till 2017, which is when the data was collected. And then there's a forecast increase in demand up until 2050. The big point here is that for the 25 years from 2017 to 2042, the forecast demand for copper over that period of time is predicted to exceed the total amount of copper that has ever been mined in the total period of human history. So these general trends do hold true for other commodities as well, particularly for those metals that are essential for electrification and the energy transition. But let's just think about that for a minute. To decarbonise, we will need more metal than all of the metal that has ever been mined. So that's pretty staggering. The next question is, why can't we fill that demand through recycling? We're such a consumer-driven society. What if we all promise to do better with our recycling at home, with our household waste, or more importantly, with our industrial waste? What if we can become more circular? That would be really good. That would be really green and really sustainable. Last year, this paper by Richard Harrington was published in Nature Reviews. It cites recycling rates in the US, which I'm going to use here as a proxy for the Western world. And we're going to look at car scrappage rates as an example of more than household recycling. So these currently sit at about 7%. Even with optimal recycling rates, so as close to 100% as we can get, only 30 to 40% of the USA's need for lithium and cobalt could be met by recycling. For copper, which is used already in so many different things and is needed for so many of the green energy transitions, we just aren't going to get there through recycling alone. So the key point here is that in the short to medium term, recycling cannot meet this demand. In order to decarbonise as quickly as our world and as our climate needs us to, we actually need to keep mining for key metals and minerals. Which brings me to my final point, I promise. The circular economy. Mining forever isn't actually sustainable. I'm the head of the minerals section of a geological survey. It's probably a bit controversial to say that, but it isn't sustainable. We do need to become more circular. Geologists in around 100 or 200 years, they will be different to now. That doesn't mean they won't be necessary, but they will be different. Maybe we'll be living in space stations, mining asteroid belts, who knows? But the Queensland government is actually talking now about a long-term transition for the mining industry from mineral producers to material handlers. Let me go back. Because recycling really does need to become more a part of our everyday. So in the current view of mining and the circular economy, ore is mined over here. This is the Ernest Henry pit up near Mount Isa. Ore is mined and processed. Opportunities are explored along this path for waste to be turned into byproducts that could be used by the mining industry itself or by other industries. This creates a circular economic model of take, make, use, recycle, or reuse. But long term, we also need to look at options such as metals leasing, where you're basically renting the metal, like you rent a car. You return it when you're finished with it. Some companies are actually already doing this. It's not such a strange idea. For industries where there are already high rates of recycling, such as aluminium, and also for precious metals like gold, the option to lease a metal through the manufacturing cycle is already in place. So in this case, metals and other materials are processed, they're manufactured, they're turned into something that we use, and then they are returned back to a materials handling organisation at the end of that thing's life, so that that thing can then be broken down into its elemental parts, and the metal can be released to go out and become something else. So this is something that I see becoming more and more common into the future, and all of our geological, geochemical, metallurgical skills being turned to in a future state, maybe not in the next few decades, but certainly in the next 100 or so. So I'm going to leave it there. I hope I've given you something to think about, and I'm looking forward to a lively discussion this evening. Thanks.
Thank you very much, Helen. Finally, I'd like to invite Will up to say a few words.
Thanks all. I didn't make a set of slides tonight because I think we've seen a fair few already, and I just want to thank other speakers because they've set up what I want to say. It couldn't have worked out better if we'd already planned it ahead of time. I promise you we didn't. So thank everybody online in the room. Brian, thanks for those opening remarks. It's great. I should let you know that when I was a kid, I wanted to be an astronomer. So maybe we swapped roles there. Look, I want to say a few things. I am an earth scientist by background, marine in marine geology and paleoclimate. I see a few paleoclimatologists, friends of mine in the audience, Neroli and Brad, maybe a few others online. So I do have a background in, in the old days, which I miss, of punching piston cores into the bottom of the ocean. And I did love that, going out into the field. I did love going out to sea, and if I ever get the chance again, I would jump at it. And so I did want to talk about earth sciences in a broad sense. And my own role now involves really being part of a group that tries to mainstream climate science, Red Cross government policy, and that includes building that sort of sense of climate risk right across our own, even our own government operations, which also, like every sector of the economy, face climate risk. And a big part of that is constantly making the case for the science that underpins a lot of the adaptation policies and tools and products that we now are delivering. We're running out climate services like the Australian Climate Service and like climate services for agriculture that actually bring that science to the user level in useful forms. And I think that is a major challenge, I think, for science. And I think sometimes one of the things that I think is a common, perhaps, misconception or conception is that when policy frameworks are put into place, there's often a sense that, okay, the science is all done. And, Naomi Oreskes' very provocative article about IPCC Working Group 1 made, in some ways, a valid point, but I would counter that by saying that once policy frameworks are put into place and science actually starts to be applied and implemented, science's work is not done. In fact, it's only just beginning, because the attempts to implement and actually deliver and apply that science raises more science questions. A great example is downscaling climate models. You may know that we try to project future climates by applying climate models. Typical climate model has a grid resolution of about 1 degree by 1 degree. That's about 100 kilometers. So all of the ACT is represented in a climate model as one grid point. So if we want to know something more detailed, we need more detailed spatial resolution in those models. So the question is, well, why don't you just run that same climate model at 5 kilometer resolution? You could try to do that, but you'd be waiting an awful long time for the answer. You could try to run it at a global scale. So we try to downscale. But in the process, we discovered that, oh, there's some physics that we really need to better understand when we're working at that time scale. Some of the convective processes, for example, that produce thunderstorms and hailstorms. So in the process of making that science more applicable and more usable, we discovered, oh, we actually don't fully understand this system. And I think we keep relearning that lesson. So that's one thing that I think I hope people come away sort of asking yourselves, if you're a student or a postdoc, what is the next question once we start applying this kind of science? And so I think that's something that I've come across in my career in the public service now for a few years. I didn't intend to be in the public service for that long, but one secondment led to another. And here I am, but it's given me a chance to really see how science plays out in the policy sphere. And it is a very challenging space. So I think earth science brings something really unique to delivering science into policy. And I think it's really important, and I'm glad that the other speakers have given a sense of the breadth of earth sciences. It's not just geology. It encompasses oceanography, meteorology, and a range of other sciences that now all come together, because many of the challenges that we're facing concern the interactions between what we commonly call the solid earth and the fluid earth. Climate change is a classic example. We're extracting resources from the solid earth and putting them into the fluid earth, and we're trying to deal with the consequences of that. And as earth sciences, we know that that distinction is not so black and white. I think Melanie showed a diagram with the asthenosphere. And we know that the distinction between something that's a fluid and a solid plays out really dramatically in the asthenosphere. We see this in glaciology. How can you tell somebody something as hard as an ice sheet is actually flowing? well, it's flowing on a very long time scale, but it is fluid. And so that's that insight that the earth sciences bring to the policy sphere. There's another insight that I think is really important that earth science training and research brings to the public and policy sphere, and that is the understanding that so many systems work on multiple timescales. We see that again, classic example, trying to couple atmospheric models to ocean models, trying to match those two different timescales is challenging, as we know. Something that Matt does all the time is try to meet that challenge. We know that a lot of things work on multiple timescales and space scales. Weathering is a great example. You know, the paradigm ever since I was learning geology is that weathering is such a long time scale that it really doesn't matter for climate. Well, now we're actually trying to manipulate weathering to accelerate it to actually enhance carbon uptake. And we also understand not just space timescales, but scale in general. That you talked about carbon removal, and the answer is we can do it. The question is, can we do it at the scale we need to do? Can we do that at gigaton scale? The total amount of CCS in the world today is something like 40 megatons. Compare that to the 40 gigatons of greenhouse gas emissions. So you're talking about three orders of magnitude, even if we cut emissions a lot. So getting that scale is important. The other thing I think that earth scientists bring to this, to a lot of these problems, is the idea of understanding complicated and complex systems. The Earth system, obviously a complex and complicated system, but again, many of the societal challenges we face come from the fact that we have one complex system, the Earth system, interacting with another complex system, which is the techno-socio-economic system, with its own complexities, its own constraints, and its own difficulties of understanding. So how do we match those two? That's one of the central challenges of climate policy. So I think that, again, we bring that. I think building literacy, both amongst policymakers and the community at large, on these idea of complex systems is something that we're really good at coming to grips with. And I think we're good, but we could be better at communicating that. And I think we also have a responsibility to gain our own literacy on the other complex systems around energy and economics, so that we can understand how earth science can help solve those problems. So I think one other thing I'll end on is to come back to applying science. I think there's a challenge for all of us in understanding how the science we produce is used. Climate science is a classic example. It's the one I know. There's a lot you can do, and we do that. We can generate a lot of data. We can generate a lot of simulations. We can do a whole lot, never knowing how that science might be used. But to really get that science to be useful, we have to start to get inside the mind of the user, the farmer, or the infrastructure project manager. So I think that we have a challenge in sort of stepping onto that other side and starting to understand how the science gets used, so that it really helps to actually solve those problems. So with that, I will leave my remarks there. Thank you all.
Thank you very much, Will. And I'd like to say a big thank you to all four panelists for taking the time to put together some really interesting discussion points. We are now going to move into a kind of more informal audience question and answer session. Any of you guys questions, we have a microphone that we'll roll around in here with. And for everyone who's online, I remind you, if you'd like to put your questions into the Q&A session on the Zoom panel at the base, we'll make sure we get some of those at least before the end of the evening. To open, I thought we'd open with one of the questions that's been on the queue already. This is from Liz Hannah. the question that I imagine might be directed towards Helen says, the contamination associated with mining creates negative impressions. Is this mostly due to dereliction of duty and disregard for environmental protection? Or is it possible that in almost all cases, financially viable mining without causing major damage is possible?
Make sure this is on. Smaller than that should be. On now? Is that better?
Yeah.
Okay. Oh, look, mining has a very, very long history. And I think that there is a lot to answer for from the mining industry throughout that long history. But the understanding of consequences are so much more evolved now than they might have been 100, going back 1,000, you know, in some cases, years. We do have really, really strong regulatory controls now in place. I think it is possible to mine responsibly and sustainably. But you need to have those controls in place. You need to be the sort of jurisdiction where people care, basically. So in Australia, I believe that we do. And each state has the laws to support that, and they have then the legislation to back them up in order to ensure that compliance. But you know, that hasn't been the case throughout all of history, and so the mining industry is tarred with that very, very long brush. There's a lot of damage to undo in terms of that reputation. So all we can do now is be better and keep being better.
Absolutely, thanks very much. Next up, is there a question anywhere in the room?
Thanks for coming together tonight, just first of all. This is more of a posing rather than a question, and it's something I've seen in discussions about climate change and renewable energies, but also in carbon capture. And it's something that sort of drives me a bit up the wall when I see it, but it's to do with thinking about reducing and cutting emissions and carbon capture at the same time. Now, often most people that are in carbon capture will never say that it's the solution. It's always going to be 90% cut emissions to zero. But often what I see is when we're talking about carbon capture, we're often saying it's not doable, it's not viable, and it's not going to work. And us as scientists, that's what we do. We work things out from a point where we have absolutely zero faith from the public that will ever work. So my point is, at the same time trying to cut emissions, we also need people to back the science going into working out how we can make that viable. Because brought up by the IPCC and many other panels before us before this, it's quite clear that we're going to need to cut emissions to nothing. But we're also going to have to account for the people who aren't going to be able to or aren't going to. So just to the panel, I'd like your thoughts on this issue and what you think about driving the science towards these solutions that nobody has hope in.
Am I allowed to start with it? Okay. Yeah, just Malcolm Turnbull came to USW about 10 years ago to talk about this topic, and he was quite playful with the audience at the time. He said, I've spent a lot of your money. I'm sorry about this. I probably shouldn't have, but I wanted to. And he said at this forum, I spent $1 billion on exploring carbon capture and storage for Australia, and I'm sorry. And it was quite a great moment in a way because he had a lot of clarity. I'm sorry, it won't work for Australia. It will work for other countries. There are other countries that have the right geological structures to bury a lot of carbon. I think Will's comment before about the scale is the big thing. And I agree with you. I mean, I want to back technologists to innovate, and I think we all want that. But my understanding, and this is not my field of research, but my understanding of speaking to the experts is that there's so much more low-hanging fruit in terms of going to an electrified grid, going to solar and storage for Australia. For Australia especially, carbon capture and storage, unfortunately, has slowed down progress toward really viable means of getting off our dependence on carbon. I think globally there'll be nations that can use carbon capture and storage, but in Australia, Malcolm's words were, I've spent $1 billion, it won't work. And there was somebody on the panel who was supporting it, so it was good entertainment, but my understanding, at least for Australia, is it's not going to work, it's not going to solve the problem, and that there's much more viable, solar and storage are the big ones that we should pursue.
I'll jump in just a bit and disagree a little bit with Matt. I agree on the problem of achieving scale, but we'll note that there are a lot of industries and processes that are difficult to decarbonize. And this is one of the things that the IPCC recent working group 3 did focus on. And there are a number of use cases where CCS in many ways does not make sense. Many people thought it would be applied to exhaust streams of coal-fired power stations. But even the exhaust stream of a coal-fired power station is a relatively dilute CO2 stream. It's about 15% CO2. Whereas there are other processes that produce more concentrated CO2 streams, cement production, steam reformation of methane to produce hydrogen is another one that produces a more pure stream. So there are some use cases where CCS may make more sense and may be more economically viable. And so I think that's where a lot of research is going. And there is a lot of research. The US Department of Energy is putting now quite a bit of investment into bringing the cost of CCS down. And the problem is the cost of capture is quite expensive. So getting that cost down to make, if we are to make it economically viable, it's important. There's a big focus on direct air capture, but if if a stream from a coal-fired power station is 15% CO2, consider the atmosphere, which is 0.04% CO2 currently, and growing, but still quite small. So I think it's sort of context dependent. And I can't see scenarios in which we wouldn't, even if you said you're only going to scale it up to meet those hard to abate sectors, you still have to grow some form of negative emissions technology, CCS or others. So I think I don't think it's my own view is I don't think it's an option anymore. I think it's an imperative.
I just want to say one of the concerns I have is I think that and I agree with what Will's saying. I think that these negative emissions have got to be part of our future. Let's do research on it. I'm all for that. I think unfortunately it's being used by the fossil fuel sector to give a sense that we're okay and that we'll be able to. And these giant vacuum cleaners that Bill Gates was investing in. And I hate seeing that this sort of blind faith almost that technology will solve the problem because some of those technologies just won't scale. As Will said, 0.04% of the atmosphere draw CO2 to clean the atmosphere, to vacuum up, to hoover up all the carbon is just not viable. And I think I just don't like seeing companies push those technologies as though we can just keep on emitting and then clean up afterwards. And a lot of environmental problems you can clean up afterwards, but carbon lives in the atmosphere for hundreds of thousands of years. Once we put it up there, it's really hard to get out. And the cost of getting it out of the atmosphere is so much greater than going to non-fossil fuel technologies.
Fantastic, thank you very much. We'll go to another question online, but in the meantime, if anyone in the room has one, put your hand up and we'll get a microphone to you to speak with it. This is a question from Liz, I guess aimed towards Melanie. It's actually not really a question, I'll try and turn it into a question. You showed the kind of decay of female representation in both mining industry and in academia. How much is that a case of losing women through time versus a reflection of the number of women graduating at those times in the past?
Oh, right, I understand. you mean that, I think,
Sorry, yeah.
no, that's okay. I think you mean that, so 10 years ago, 20 years ago, we had less women graduating. And so how can we expect our numbers to look good at level D now, because it takes sort of, 15, 20 years to get to this. Yeah, cool. Yeah, so if we had evidence that things were getting better, then I would feel a lot better about that. I don't think, so I think we're seeing, we're still seeing, we know that in, so that chart I had from the census data, we know that in 2006, we still have about the same amount of women in our undergraduate degrees as what we have now. And so, that's sort of 15 years ago now. And so they should be at level, B or C in academia, kind of work that out. And so we're not really seeing that 40% retained at level C or level B. So I just don't think the evidence is there, is that we just need to wait it out. I think we're not seeing substantial improvements in our numbers, and we're not seeing any flow through to the earliest levels of academia yet. I feel like it does feel like there's been a bit of momentum in this area in the last maybe 4 or 5 years or something. I think that, we felt that with Me Too, and, it seems like there's a lot of action on trying to create more gender equity. And so maybe we'll see that follow through, but I haven't seen any evidence in the numbers yet.
Great, thank you very much. Next up, Mary.
Yeah, I had a question for you as well, Melanie, on the same topic. And I guess I came through as a student at the point in time and was saying, oh, look, we've got pretty much 50-50 male and female students. This problem will work itself out, and it clearly didn't work itself out. So I'm wondering, sort of, over what sort of timescale can we expect to actually get to the point where in neurosciences we're retaining women at the sort of the same level as we're graduating them, and what are the best actions that we can be taking, and are the actions within neurosciences, is there anything specific to neurosciences as opposed to just science in general?
Yeah, that's a great question. And so it's really, because you're a level E, right? And you have 50-50 gender split in your classroom. So it's like the perfect example, because there's not many level E professors, there's not many women professors in Australia, but anyway. So what are we looking at? Yes, well, we had this great, some great modelling done at JCU recently, which took the proportion of men and women that we have in the College of Science and Engineering at the moment, and then forward model what it's going to look like in 10 years with different manipulations. So if we hired women at the same rate as men, and if we retained women at the same rate as men, and if we promoted women at the same rate as men, and none of those things are currently happening, but it just showed the effect of all of those. And it just showed, if you do like any one of those, then you make things a lot better. And if you do sort of 2 out of the 3, then you've solved it in 10 years. I was like, oh my, that's amazing. There's a solution. Like, you just have to retain and hire and promote women, like, it is so obvious, but then yeah, you have to get at the underlying, issues, like why aren't they staying? Why are they all leaving? Well, at JCU, they're leaving, in my college, they're leaving at sort of level D, that sort of. So that really actually gave me hope that there is a solution if we can get to these underlying issues. So I think that in some cases, our workplaces weren't designed with women in mind. They're not, and that becomes evident in lots of different ways in earth science. Like, we take students on field trips to remote places, and we've got 100 students out in the field in a place with no bushes. And it's like, yeah, you just figure out the toilets yourself, ladies. Like, what are they supposed to do? It's just really tough. And so we just need to be more mindful of things like that really turn students off our discipline, and sort of make them feel like that this is not the place where they belong. That sounds like a minor thing. It is a minor thing, I guess. But I think for some students, it's the reason that they leave, and some, indeed, some academics as well. So I mean, that's just one example. There are many. So I'm really hopeful that it's going to get better if we are more mindful of the problems that we have and how we can solve them.
I was just going to ask something about the same topic. I'm a generation older,
and there were 3 girls in my first year class and 150 guys. So from that time to the time that Melanie went to university, something great happened, right? What was it that happened, do you reckon? And why now is that turning column going back down?
I don't know what that thing was that happened, but that's sounds cool. It sounds like it
I
sounds
think
like
the data needs to go back further, and you need to really analyse it a bit more.
yeah, absolutely. Yeah, see if those data are available. And yeah, I think that part of what we need to do to drive those numbers, back, well, to get those student numbers higher, or get the representation higher, is to be looking at the causes of why people leave. I think we have the research that tells us why it is people are leaving. There are social scientists, psychologists, people who work in education research have been looking at this in science for a long time, and we kind of know I think we know that what we need to do. It's just a matter of implementing it, I believe.
Okay, thank you. Next up we have, it's a bit of a two-parter from Ram. It's probably directed towards Helen. Has there been any conversation regarding the transition to green mining and decarbonising the mining process? And more broadly, what are some of the challenges we could face if we do decide to transition to greener mining?
Absolutely, there has been that conversation. It's happening globally, it's happening within Australia. So if anybody that owns shares is an investor will have heard the term ESG, so environment, social and governance. And these are social, or is it sustainability? Anyway, ESG, it is driving investment trends around the world. It is driving policy trends, and anything that's driving those two is then going to drive industry, and it's going to drive outcomes. So, so green mining is the sort of thing that consumers are demanding out of their green products. Nobody goes and buys, well, some people might go and buy an electric car because they want to be like the cool kid on the block, but most people are going to go and buy an electric car, as an easy example, because they care about the environment, because they don't want to be polluting as they drive to work or run their kids around to sport and that kind of thing. So you don't want to hear that, some child died to get the cobalt out of the Congo to make the battery that's in your electric car, as an example. So there is an increasing movement towards traceability of raw materials that goes into the very, very complex products, manufactured products that we use every day. So this is where blockchain comes in as an example of, and I barely understand blockchain, I will admit. It's like one of those things, what is that? But it's basically a system to trace supply chains, to have certification along every step of a supply chain, so that you can take your electric car and you can, if you really wanted to, you could go back and trace where every component and ultimately to the raw materials that make up that, where it all came from, and what was every step of the way, every manufacturing step, what are the green miles, how far has that material been transported around the world from Australia or the Congo, I don't know, all the different places where that material has been mined, to then where's the manufacturing centre for the different components, and then the other manufacturing centre, so it's the car manufacturer in Europe or in Japan or Korea. So there's a lot of complexity in that, and that all of that demand, and the demand for knowledge essentially filters back down to, well, if consumers, if the users of those end products demand that they are green, then every step of the way is increasingly being scrutinised. And so that is driving legislation for green mining. So I mentioned in my talk the battery passport for Europe. That is legislation that is coming in to Europe in 2026. And it means that all the raw materials that make up batteries for cars into the European car market will have to have ethical certification for where the source of those raw materials is, and they will have to include a certain percentage of recycled material. So that is going to become law, you know. So we can't then get around that. So anyone that wants to sell their raw products, any mining company that wants to sell those products to BMW or VW or whoever in Europe must make sure that their raw material right from the start meets those credentials. So that Europe is a first mover in this space, but it will, you know, it will filter to everybody as that becomes possible. As one jurisdiction says we can do this and we have done it, then the others will follow suit. So absolutely, I think green mining is possible and it's on the way. And what was the second part of the question? I forgot.
I think you pretty much covered it. That was great.
Okay,
Thank you very much. Richard, you have a question?
Yes, thanks everybody for raising all these issues about earth sciences in the 21st century. And one of the early graphs was the declining enrollments within Australia. Do you, the panel, feel we don't have to worry about this? You can take a benign view. Australia's often done this. We'll just recruit the health workers from Bangladesh or the United Kingdom. Doesn't matter, let the market take care of it. Or internally, like the doctors, control the number of graduates, so you can restrict and make very attractive the salaries that those professionals earn. But the declining enrollments, is that something we worry about, or don't worry about it at all? They'll just drift in from overseas with the appropriate visa and the appropriate placement.
I worry about it a lot, and probably everyone working in academia worries about it a lot, because if we don't have students in our classrooms, the reason for us being there sort of reduces, as we saw, you know, over the last couple of years. It's really, but you know, the thing that also really gets to me is that there are all these people who really want to be geoscientists, and if they knew about it, right, they would love it. And we get them in at first year, they're coming in because they just have to pick up an elective, or, you know, and so they learn about geoscience, earth science for the first time, and they're converted, they become geoscientists, and they, you know, become academics and whatever. They just absolutely love it, but we're missing out on so many people because they don't know that we even exist. And so I think I would just really like, you know, the young people, you know, in high schools and coming into university to have a sense of what earth science is and how amazing it is to understand the earth around us. And I think just sort of from a pure science perspective like that, it kills me that our student numbers are reducing, and I don't think that we should accept the status quo. Not even if we're not even considering like economic reasons or, you know, industry related reasons, just because our discipline is important and it's amazing, and I think more people should know about it.
I'll just add one comment to that and just say that I just to add to what you said, Melanie, which is really quite powerful, and just say we have to start earlier.
Yeah.
I think and integrate earth sciences into other disciplines. Often Leah in the audience, and she's done some work on this. So we've heard
curriculum, and since 2015 we've got high school in 11 and 12 science.
Yeah.
So we've got pivotal enrollment.
Yeah.
The tension is getting uptake and expertise in schools, because there's still a reluctance to teach it because the teachers are not confident in their own understanding. So we have a role to play as universities and supporting schools to do that.
Yeah, I'll just add that we don't do a good job of poaching people from other disciplines. We should do a better job of that. We should be saying to students, oh, you're a physics major? Awesome. We need you in earth science, or a chemistry major? Great, come on over here.
We're short in all those areas too.
Well, and I was going to say that this reflects overall problems in STEM. But I think we should do a better job. And I think about climate science itself, right? The area that we work in. And I remember some question came up, you know, who is a climate scientist? And my answer was, well, in some way, nobody. We're all we all came into this from other disciplines, geologists, or chemists, or mathematicians, or something. And so in a sense, I think it would be great if earth sciences just, you know, cast that wide net and say, oh, you're a mathematician, awesome. You can be an earth scientist, because actually we need that.
Yeah, it's a great question, and I sense we're ending up pretty soon. So it's a great question to pose. We're all concerned. That's why we probably travel down here, because we're concerned about that. I don't like that metric. I think Brian made the comment a lot. I mean, the maths colleagues I have, I used to be in a maths school, but I'm now in an earth environment school, and mathematicians seem to decline as well. So I think part of it's a lack of awareness of the careers that are out there. You know, people think of earth sciences and they think that's going to be going to the field with a hammer and some equipment and digging up, or you know, they don't understand the huge number of career opportunities. And part of this is as was mentioned earlier, you know, going to schools and giving those talks. The Earth Environment program that was developed was fantastic. So it adds visibility at the school level. Yeah, we need to do something about making it more visible and getting that progression from school to university to careers.
Amazing. Thank you very much, everyone. I'm afraid we are now slightly over time. We do have more questions still coming in online. So keep firing them in. We'll record them, get them written down at least. Anyone in the room has anything they'd like to talk about afterwards, we're going to take the discussion out back. There'll be some more drinks and some more food and so on. I'd just like to finish by saying, first of all, a big thank you to our 4 panelists. Sorry to drag you down here, put you on the spot in front of all the right answers, but you've all done a really wonderful job and we really appreciate it. The final thing I'd like to say is a big thank you to the organising team, to Jess, Shub, Boone, Larissa, Tia, who's hiding in the room at the back up there. Thanks for making this happen. I know you all pulled together and did a lot of things that weren't necessarily in your job description, so I much appreciate it, and hopefully we can have a good conversation moving forward from tonight.